Okay, let's look at some trigonometric identities with using complex numbers. So let's think about cosine 4 theta is equal to 8 cosine raised to the quadric minus 8 cosine squared theta plus 1. Okay, so let's see how we can solve this particular problem. Well, the first thing we need to do is we need to say let z equal to cosine theta plus I sine theta. The reason you can use this polar argument form is because we look at the positioning of the 4 here. Now, if you remember from the Moore's theorem, we know that we can now apply the Moore's theorem to get that 4 into the position in front of theta. So let's see if we can do that. Then we can say, well, z to the 4 is going to be, I'll just write the full one anyway. Let's say it's r cosine theta plus I sine theta. And we can raise all of this to the 4. We can then distribute or apply the Moore's theorem. So let's just say apply the Moore's theorem or the Moivre's. So I have r to the 4 times cosine 4 theta plus I sine 4 theta. Okay, so look at what we just discovered. We just discovered this cosine 4 theta, and it's very similar to what they're trying to ask us. Okay, so what we can do now is we can apply the binomial theorem, and then we can try isolate the cosine, because we can notice that by looking at our initial problem only consists out of cosines. So we know at some point we're going to have to take all the sine values and make them cosine values. So let's see if we can do that. Now we can apply binomial theorem to the following problem. So we're going to say is equal to, since r in this particular case is 1, right? We can then say, well, it's just going to be cosine theta plus I sine theta. We're going to raise this to the 4. Let's apply the binomial theorem here. So first things first, I'm going to construct a little Pascal's triangle. 1, 3, 3, 1. 1, 4, 6, 4, 1. These ones also correspond to 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Okay, now that we know that, we can now use this little technique where I add 5 brackets, 5 groups of 3, and I'll explain in a second why I do that. If you've watched the binomial theorem video, you should know. However, it's important to understand that Pascal, we can think about start counting at 0. So let's think about this. So that could be 0, 1, 2, 3, 4. You see, so if I count 1, 2, 3, 4, 5 on the side here, I can see, well, there's 5 numbers. And I need to account for all 5 of these numbers, right? I need to account for 1, 4, 6, 4, 1. So if we count them, 1, 2, 3, 4, 5, you can clearly see there's 5 numbers. Okay, now in your first bracket is the Pascal value. In your second bracket would be A, and in your third bracket would be B. So what exactly does A and B mean? Well, we can think about it as A plus B raised to the n. So in this case, A would refer to cosine, and then B would refer to sine, or I sine. So let's go. Our first, we place in the Pascal values, 1, 4, 6, 4, 1. Next, we place in the A, which is cosine theta. Cosine theta. We have cosine theta. Cosine theta, and then cosine theta. Next, we have I sine theta. I sine theta. Okay, now the next step that we have to do is we're going to count in ascending and descending powers This is just applying the binomial theorem. So, So we have, let's say we got 4, 3, 2, 1, 0. So your A, you start by the highest and you count down to the lowest. And for B, you start by the lowest and count down to the highest. Just a little technique. And a little reminder is that when you add these two values together, so 2 plus 2 is 4, it should be the same as this particular value over here. Okay, so let's say, for instance, for argument's sake, I made a bit of a mistake and I added a 3. In this case, I can see 2 plus 3 is 5. So that's obviously not going to work. So let's go to, now we can solve this binomial theorem. Just apply what we know. So it's going to be cosine 4 theta plus 4 times cosine theta raised to the 3. I could place that 3 maybe on the inside. Times I sine theta. We can say plus 6 cosine squared theta. By the way, I'm just multiplying these ones in, right? Times I squared sine squared theta plus, in this case we have 4 times cosine theta plus I sine theta, that's raised to the 3 theta, and then I is also raised to the 3, and then finally we have plus I raised to the 4 sine raised to the 4. Okay, the reason I don't do this one is because anything raised to the 0 is simply 1. Now we can simplify this very long expression. I'm going to say cosine 4, but before I do that, we can say, well, let I raised to the square equals minus 1, right? One of our first identities that we know from complex numbers. So in this case, I have plus 4 cosine cubed theta times I sine theta plus, or in this case, well, now I can see that minus 2 over there, look, this minus I squared will become minus 1. So this will then be minus 6 cosine squared theta times sine squared theta. In this particular case, it's going to be minus 1 times I, so that becomes minus 4 cosine theta times I sine theta. And then finally, I have, if I have I to the 4, that will be minus 1 times minus 1, which is plus sine 4 theta. Okay, see what we got over here. Now that we have this expression, the next thing I want to do is I want to group my real numbers or my real values, and I want to group my imaginary values. So let's go find all the real ones. That's real because we can see there's no I, so you identify them by looking at which ones have I's and which one have no I's. This one over here is real, and this one over here is real. If I look at these two, that has an I, and that has one I too. So now I'm just going to rearrange it very nicely. Cosine 4 theta plus, oh, excuse me, that was a minus, minus 6 cosine square theta times sine square theta plus sine 4 theta. And for this case, I'm going to say plus, and I'm going to factor out an I from both these imaginary parts. Okay, I'm going to factor out the I. So I will then be left with 4 cosine 3 theta times sine theta minus 4 cosine theta times sine theta. I might have missed a exponent somewhere. I don't think so though. They may have. Let me just double check quick. There's a 3 missing here. Okay, sorry, there's a 3 missing there. Because I don't have a sign to the 3. So that makes perfect sense. Okay. Now, what do we know? So now we can say equate the real parts. So equating the real parts, that would mean that cosine 4 theta, by using the Morse theorem, is equal to this box. I'll show you now exactly. Is equal to this expression right here. So how do we know this? Well, if I think about I sine, or if I think about the following, if I think about z is equal to x plus yi, I can see that my real part has no imaginary component, and then I can see my y with the imaginary part has some component to it. Although both of them are real numbers, I can clearly see that the second part of the equation, I can clearly see there is some I. I belong to both this expression and this expression. So that is my imaginary part. So let's say, the argument's sake, you were given sine 4 theta. You will then put this, the imaginary component, equal to sine 4 theta. Okay, but since we're working with cosine, and we can think about our original polar or modulus argument form, we can think about cosine theta plus I sine theta with some r, some modulus. We can clearly see that this is the real part. So now I can set the real part, the two real parts equal to one another. That's going to be cosine 4 theta minus 6 cosine squared theta times sine squared theta plus sine 4 theta. Okay, now if I look back at my original problem, I saw that my original problem only had a bunch of cosines in them. So that means I need to take every single sine expression to cosine. I could do that very easily by using the Pythagorean theorem identity. So in this case, I will apply the Pythagorean theorem identity to cosine 1 minus cosine squared theta. And then here I can apply the Pythagorean theorem identity too. I could say, well, this is going to be 1 minus cosine squared theta squared. How do I know this? Because essentially sine 4 theta can be rewritten as sine 2 theta raised to the 2. And then I know that sine squared theta plus cosine squared theta is equal to 1. So if I subtract cosine on both sides, I can see that sine squared theta is equal to 1 minus cosine squared theta. Okay, so now I'm going to simplify. So let's go simplify this problem. That's negative 6 cosine squared theta plus 6 cosine squared theta plus, if I just use my basic formula here, where we have a plus b squared, actually a minus b squared, sorry. We can say a squared minus 2ab plus b squared, difference in squares, I could just use that. So that's going to be 1 minus 2 cosine squared theta plus cosine 4 theta. Finally, adding my like terms, I can see I'll identify my like terms. So that's a like term, that's a like term, and that's supposed to be a like term. I see my mistake. because I remember from the previous answer there was an 8. So the mistake I made there was I multiplied the 6 and the positives correctly, but I did not multiply the cosine squared correctly. It's a bit of a mistake. And that's actually one way how you can double check your answers. So that then gives me 8 cosine 4 theta. If I use that, and that already, I'm then left with minus 8 cosine square theta plus 1. And that will be my final answer. Now, obviously, we can simplify some steps here, of course. I just wanted to show exactly how I would get this answer. Okay? So I'll do one more example. Let's look at another one. But let's look at a bit of a more difficult one. Okay, so let's say we are given maybe the following. We're given cosine theta plus I sine theta raised to the 4, and they ask us to find, question A, find the imaginary part, and then B, they ask us to find that sine 4 theta is equal to 4 cosine theta sine theta minus 2 sine cube of theta. Okay, so they ask us the following. So first things first, we will just we'll just apply. So let's apply the binomial theorem. I think I spelled that incorrectly. Binomial. Oopsie, no I. So apply the binomial theorem for the following. We could say that cosine theta plus I sine theta raised to the 4 is going to be equal to, we know it's cosine 4 theta plus, what was that? It was 14641. So it'll be then 4 cosine cubed times I sine, right? Times I sine theta plus, I'm using the same technique as earlier, by the way, but this time I'm just doing it in my head. Eventually with some practice you'll become quite good at it. Times I squared times sine squared theta plus, we're left with 4 cosine theta times I to the 3 plus, times sine 3 theta. And then finally we got I4 sine 4 theta. Okay, this is what we got. So if I simplify this, I'll just look back at one of these examples. So we had, just double check, because it in this particular case it's going to be the exact same one as earlier. So I'll just focus. Okay. It's going to be cosine 4 theta minus 6 cosine square theta times sine square theta plus sine 4 theta plus plus I 4 cosine 3 theta times sine theta minus 4 cosine theta times sine 3 theta. Okay, so there we go. There's our imaginary part. We got that lock and loaded. You can apply the same thing, by the way, if it's raised to the power of 5. You just used 1, 5, 10, 10, 5, 1. If it's raised to the power of 6, it's going to be a monstrous equation, but a lot of identities you need to apply here. But all of them you solve exactly the same. It's literally the same technique over and over and over. Okay, so we got our imaginary part. So now we need to show the following. We need to show that sine 4 is equal to 4 cosine sine theta minus 2 sine cubed theta. Okay, so let's equate the imaginary part. Let's equate the imaginary part. So the imaginary part was sine 4 theta. Again, we just applied the Moivre's theorem here. I'll just quickly redo it. So we can say let z is equal to cosine theta plus I sine theta. Then we have if z to the 4 is equal to cosine theta plus I sine theta raised to the 4. Remember, we simply raise the modulus also to the 4, but in this particular case, we don't have a modulus, or our modulus is 1 at least. So if our modulus is 1, it's just 1 raised to the 4, which is just 1, right? Okay, so now we can see we got our imaginary part there, so we can set that imaginary part equal to this imaginary part. And now we have to think a bit. This is how we want to structure this. Unfortunately, sometimes you can't just jump in. The issue with that is, if you just jump in, you might run into a dead end after a couple of tries. So let's see, what have we got here? Okay, I'll tell you how I think about this. We can see a 4 cosine 3 there. We obviously only need 1 cosine, so that's definitely changing to a sine. One particular problem with that may be, what? What could be a problem? Let's try it. Let's try and get rid of this cosine real quick. I don't think there'll be an issue. So it's going to be 1 cosine times 1 minus sine square theta times sine theta minus 4 cosine theta times sine cubed theta. So the cube we want to leave, right? Because we need a sine cube. We can clearly see that. We need some sine cube. So that's fine. Maybe we also want these two. We want these two to be the same. So I want to keep that and that. I don't want to touch it, right? The reason I don't want to touch it is because I can already see that's in my final answer. So that's fine. So the only other option is to distribute this sign in. So let's try and get rid of it. It's going to be sine theta minus sine cubed theta minus 4 cosine theta. Okay, now we should be able to see the answer. Next, I will factorize a 4. I'm going to factorize these two, that and this one. I'll factorize both of it. So we get 4 cosine theta sine theta minus sine cube theta, and then we will be left with minus 1 minus sine cube theta. So now I can add the like terms. Cosine theta times sine theta minus 2 sine cube theta. Okay, there we just proved the identity. We can clearly see that these two are the same. Yep, they look very similar. And now I'll put one more on the board, but you can try this. And it's going to be a bit of a challenging one, so I'll guide you how to do it. You can obviously confirm your answer by looking at the resultant, right? Okay, so let's see. Minus 20 cosine cubed theta plus 5 cosine theta. Okay, I'll guide you on how to do this. First things first, we can clearly see there's a 5 in there, so we knew that the Morse theorem plus I sine theta. We know that the Morse theorem is raised to the 5th, so it's going to be cosine 5 plus I sine 5 raised to the 5th. So then we have cosine 5 theta plus I sine 5 theta. So now, after applying the binomial theorem, we can clearly see that this, if I just compare it, x plus yi, if I just compare this x, I can see that my real part is going to be equal to the 5 cosine theta. So we can then say, well, the cosine 5 theta is going to be equal to the real part of my binomial expansion. Okay, the real part will be equal to the cosine 5 theta will be equal to the real part of my binomial expansion. So I will also then just finally leave you with the constructed Pascal's triangle. So that's 1, 1, 1, 2, 1, 1, 3, 3, 1. By the way, again, I just get that by adding the resultants. 1, 5, 10, 10, 5, 1. So now we're just going to have 6 groups of 3s, and that should be it. Okay, best of luck with this problem. Final tip I will leave you with is, if we look at this answer, I can clearly see there's a cosine, cosine, cosine. There's no sign of sine. So you are most likely going to have to use something like this. Most likely. There might be some other identities that you could use. So you're most likely going to be using this one, sine squared theta minus cosine squared theta, to get rid of all the sine squared thetas. Okay? Okay, best of luck.